Hello, very good morning to one and all. I welcome you all to this online classes. Today we are going to discuss about electric field lines. In the last class we discussed about the electric field. Now we will see the electric field due to a point positive charge which is located at origin O. As we all know that a vector, so electric field is a vector which is represented with an arrow like this, a tail and a head, and the arrow length is proportional to the magnitude of the vector. This is the fundamental thing about a vector, right? So here the electric field and its direction is represented with an arrow. So the arrowhead indicates the direction, and arrow length is in such a way that which is proportional to the magnitude of the electric field or the strength of the electric field. So here given the magnitude of the electric field is proportional to the arrow length. It is directly proportional to arrow length. Now, as we all know that the electric field is inversely proportional to the square of the distance. That is, as we move away from the charge, the electric field decreases. So here, as we are moving away from the charge, the arrow length goes on decreasing. So arrow length is an indication for the magnitude of the electric field. As we move far away from the charge, the arrow length decreases, showing that the electric field strength also decreasing because of this dependence. E is inversely proportional to the square of the distance, right? And all these vectors, so these are the electric field vectors, they are pointing radially outward. So here, if we keep a positive charge, so these arrows indicates that the force experienced by the unit positive charge which is kept at the tail of the arrow. If you keep a unit test charge, the force experienced direction is these things. Right. Now join all the vectors, electric field vectors, which are in one particular direction. Suppose by joining all these vectors which are in this direction, what we will get is an electric field line. Similarly, by joining all these electric field vectors are along one particular direction, giving rise to the electric field line. Right. Now, by doing this, joining the vectors and forming the electric field lines, we lost information about the magnitude of the electric field, because the magnitude of the electric field will be given by the arrow length. Now what we have done, we joined all the vectors. Now we got only a line, electric field line. So how to know the magnitude of the electric vector or electric field at a different points? Now, for this electric field lines, we will consider density of field lines rather than the arrow length. For the vectors, the magnitude is given by arrow length. And for the electric field lines, we will consider the magnitude of the electric field is given by the density of field lines. So what is meant by density? Density of field lines is nothing but the number of field lines crossing per unit area. The density of field lines is nothing but the number of field lines passing per unit area, right? So close to the charge, the electric field is strong, because close means R is a small, electric field is strong, and the density of field lines are also more. So that is why the electric field lines are closer. Let us consider an arbitrary area element A1, let us say A1, and also consider one more area element A2. So whatever the lines which are passing through area element A1, the same number of lines are also passing through area element A2. So in that case, density of field lines, which is given as the number of field lines passing per unit area. So let us say through A1, I am saying 100 lines are passing. So density of field lines is nothing but number of field lines per unit area. So number of field lines are 100 and divided by A1. Similarly, the density of field lines passing through area A2 can be written as N by A, let us say 100 by A2. So to understand it, I have given this area A1 as 10 units and A2 as 100 units, let us say. So here this ratio, the number of field lines per unit area here is 10 and here it is 1. So what is number of field lines per unit area? Nothing but the density of the field lines, density of field lines. So here in area element A1, the density of field lines are 10 and in area A2, the density of field lines are 1. So it shows that the electric field strength, we said that the electric field strength depends on this density of field line. So here the electric field strength is strong and the electric field strength here is weak. So that we can understand electric field density of field lines will give the magnitude of the electric field. So close to the charge, the electric field is strong and density of lines is more. So they are very closer. The electric field lines are closer. Far from the charge, yes, we know that electric field R is more, electric field is less. So electric field is weak and the density of lines is less. So the electric field lines are far apart. That we have to understand in case of electric field lines, right? Now you said that the density of field lines represent the magnitude of the electric field. So I have drawn these many electric field lines around the test charge, but around the charge I can imagine infinite number of points. So let us say if I observe a point here, so if I keep a unit test charge, the force experienced by the test charge due to electric field is pointing in this direction. Similarly, if I imagine a point, the electric field due to charge exerting force on the test charge in this direction. So I can imagine an infinite number of electric field lines around the source charge. I can imagine infinite number of field lines. So here I have drawn these many, but somebody have drawn more field lines. So what is the quantity which we need to consider is the relative density. So the relative density of field lines. So this is the density of field lines through A1 area and this is the density of field lines through A2. So what we'll consider is relative density which is changing from region to region. This quantity is important. What is that? The relative density in different regions will be different. So here we got for these two regions 10 by 1. If I change the region, this ratio also changes. So that we need to remember for the comparison. So relative strength of the electric field will be knowing using relative density and different regions, right? So here we have drawn the electric field vectors and the electric field lines on the plane of a paper. But if you consider a charge, its influence, so if you consider a source charge, its influence is around the charge. So the electric field vectors and the electric field lines are spread in space, that is in 3 dimension. So in 3 dimension, if you want to represent the electric field lines, so we have given the density of field lines as the number of field lines which are crossing per unit area and the area is perpendicular to the field lines. Always we have to consider the area element perpendicular to the field lines. So that definition is appropriate because this is for 2 dimension and for 3 dimension if you want to know the electric field at one particular point, so this definition, the number of field lines per unit area where the area is perpendicular to the field lines is appropriate, right? And we know that electric field is inversely proportional to the square of the distance, and area is directly proportional to the square of the distance, right? So one is inversely related and one is directly related. So here we can say that the number of field lines crossing in a unit area remains constant whatever may be the area element, distance of the area element from the charge, that we can see here. Let us consider the charges at O, and I consider at two different points P1 and P2 where I want to calculate the magnitude of the electric field. So I consider a area element delta S1 which is passing through point P1 and area element delta S2 which is passing through P2, and this P1 and P2 are at a distance R1 and R2 from the source charge O, right? So here observe that this area elements delta S1 and delta S2, the number of field lines which are passing through S1 and the number of lines passing through S2, they are same. That is the thing we have written. The number of field lines crossing per unit area remains constant whatever be the distance of the area element. So here delta S1 is the area element which is located at R1, and delta S2 is the area element located at a distance R2. So these are located at different distances. Still the field lines remain constant. So we'll understand this equation. So we said that the density of field lines is nothing but number of field lines per unit area, and we are saying that for any area element the field lines remain same, right? So n can be written as A into density, let us say density D. Number of field lines is equals to area times the density, right? So consider the first area element which is close to the charge, So here the area element is small, so here it is close, means the electric field lines are closer, indicating the strong electric field. So the electric field is large. For the area element S1, area is small, but the electric field lines are very closer, means the density of field lines is more. So here the density is large. Now, whereas let us say this is N1. Now, the number of field lines for the case of S2 can be written as area is large. Now, the area element is large. And what about the density? Here we can observe the electric field lines are far apart. So, showing that the electric field is weak. So, the electric or the density of field lines are small in such a way that, so area is small, density of field lines are large in for the area element, and for the area element 2 the area is large, density of field lines are small, so that the product remains constant. So N1 is equals to N2. This is the thing what we have written. Number of field lines passing through any area element remains constant whatever may be the distance. We can observe here R1 is small. R1 small means electric field is strong, and if R1 is small, here the area element is small, so here E is strong, area is less. Whereas for the second element, E is weak, nothing but density of field lines is less, area element is small. So they compensate because E is inversely proportional to distance and A is directly proportional to R square. Always the field lines remain constant. Why? Because the area has square dependence and density of field lines, nothing but the electric field, have inverse dependence. So the product, the number of field lines remains constant, right? Now we started saying that the electric field, at different points indicate the strength of the electric field. So these are the directions showing the how a test charge experience a force, right? So if you consider the electric field lines, if the electric field lines are crowd, means very closure, indicates the electric field is strong. If the electric field lines are far apart, well separated, the electric field is, or magnitude of the electric field is weak, right? So here in this figure, I consider two different area elements whose areas are equal, Now by so area is same. So density of field lines is nothing but number of field lines per unit area. So for both of them the area is same. Then what about the number of field lines? In the case of R, the more number of field lines are passing through, whereas in S, the less number of field lines are passing through. N, let us say here it is 2 and here it is 1. So it shows that this ratio, density of field lines, because area is same, the density of field lines is more in case of R and density of field lines are less. So here the electric field is strong at R and electric field is weak at S, right? Now we are going to relate the density of field lines with area or the solid angle. We are going to relate the density of field lines with the solid angle or with the area, right? We will see. So what is a solid angle? So in a two dimension, let us say if you are discussing the things in two dimension, so in that case, if I consider an area, an line of length delta L, which is at a distance r from the origin. So this is nothing but arc of length delta L, and the angle made by the arc at the point O is nothing but plane angle. So in two dimension, the plane angle is nothing but arc length by distance r. But in case of a three dimension, if I want to know the angle made by a plane, let us say this is a plane delta S, which is making an angle at the point O, which is at a distance, the plane is at a distance r units from the point O. That angle is given by solid angle delta omega. For a circle, let us say for a circle, so it's a two-dimensional object. So an arc which is making an angle at point O, this is given by plane angle. It is given by plane angle. If I have a sphere, in that case, the angle made by a particular plane at the center is given by the solid angle delta omega, right? And solid angle is represented with the formula delta S by r square. Delta S by r square. What is r? The distance of the plane from the origin, right? Now, so this is the thing. We already said we consider 2 points P1 and P2. Now at these points we are going to calculate the density of field lines. So to measure the density of field lines, we require the number of field lines and area, right? So here for a given solid angle, so here I consider these two area elements are making the same solid angle, and I said that for these two area elements the number of field lines are same. Whatever may be the distance, the number of field lines are same. So for a given solid angle delta omega, the field lines passing through P1 and the field lines which are passing through P2, they are same. Delta omega is same for both P1 and P2. Now what is the area delta S1? So the delta S1, the area element delta S1, which is subtending an angle, solid angle delta omega, then the area at P1 is given by delta S1 is equal to, from the formula, solid angle is equals to delta S by R square. So the area subtending an angle delta omega at point P1. P1 is at a distance R1. So in that case, delta omega into R1 square. Similarly, the area subtending an angle, solid angle delta omega at P2 is given by delta S2 is equals to delta omega into R2 square. So this is the solid angle which is same for both the area element, and for that given solid line, the field lines which are passing through area element S1 or S2, they remain same. Let us say the number of field lines as n. Now we are going to calculate density of field lines at P1. So density of field lines at P1 is equals to nothing but number of field lines per unit area, n by area is nothing but delta omega into R1 square. Similarly, the density of field lines at P2 is n by delta omega into R2 square. It shows that R2 square. So at P1 and P2, so what is this density of field lines? Nothing but the electric field strength, indicating the electric field strength. So here n and delta omega is same for both P1 and P2. Indicates the electric field has inverse square dependence. So we said that density of field lines, it gives the magnitude of the electric field, and here by let us say if you consider the ratio, what we can get is 1 by R1 square. So R2 square by R1 square. It shows that density of field lines gives the electric field, and the electric field has a inverse square dependence. It has inverse square dependence. And this concept of electric field lines was developed by Faraday. And here, this is a non-mathematical way of representing the electric fields around the charge, right? And initially, he named these lines as lines of force, but later we adopted that these are electric field lines, not the lines of force. We given a name as electric field lines. And here, for the point charge, we got the electric field line as a electric field lines, but every time we will not get a lines. The electric field lines are curves spread in space in 3 dimension. Suppose, so this is the electric field line. Suppose if you have a curve and the electric field is pointing like this. Suppose if I want to know what is the electric field at one particular point, so what we have to do is draw a tangent to the curve at that point. So this indicates the force experienced by the unit positive charge, and in which direction I have drawn tangent? In the direction of the electric field. So for the case of electric field curves, draw tangent at that point will give rise to the electric field direction, and the tangent is drawn in the direction of the electric field. Now we will see the electric field lines due to some charge configurations. So here we consider a point positive charge. So here if you keep a point positive charge, the force experienced by the unit test charge, positive test charge, is in this direction. So here the electric field lines are moving from positive, from the charge to infinity. It shows that the field lines are moving away from the charge and end at infinity. So here this effect we call it as hair dryer. It pushes with a strong repulsion, it pushes the test charges away from the source. So it is called hair dryer effect. So because if you want to dry a hair, the air is blown in such a way that they will separate the hairs. So it is the hair dryer effect. Now for the case of a negative charge, so the positive charge is trying to move towards the negative charge because of attraction. So if I keep a test charge, positive test charge here, the force experienced by the test charge is towards the source. So in this case, the electric field lines start from infinity and end at source charge. So here this is acts like a vacuum sucker which sucks the dust particles, everything. Similarly, if I have a positive test charge, it attracts the test charge towards it. So this is a vacuum cleaner effect. Now if you have a two positive charges, so in this case, if I have, suppose if I keep a point charge here, now what we have to consider is electric field is due to superposition of charge 1 and charge 2. So E1, electric field due to charge 1 and electric field due to charge 2. So at this location, the unit positive charge, test charge, experiences strong repulsion force. So it moves away from both the charges. So for a positive charge, always the electric field lines move away from the charge, right? Now, if you have a dipole, what is meant by a dipole? That we will see. Let us consider a charged body which is having a negative charge, and let us consider a body in which I have atoms, right? And in the atoms we have electrons and positive charge, right? So if I keep this charged body close to the another body here, because of this negative charge, the electrons are repelled and then move to the other side, and the protons are attracted, so they move little bit shift. So an equal amount of charge electrons, if suppose two electrons are shift away from the charged body, so deficient of electrons will create a proton, nothing but the positive charge. So here a equal amount of charge is separated by some distance, creating a dipole. This is nothing but the electrification by induction process, in which we have seen a accumulation of charges is a fraction of charges on the surfaces. So this effect, we said that it is a polarization effect. Similarly here also, if I have a two equal and opposite charges separated by certain distance, and the positive charge always try to repel the unit positive charge, and the negative charge is always trying to attract the positive test charge towards it. So see here, so always the electric field lines move from positive charge to the negative charge. So always they move from positive to negative, whereas if you have a single charge, the electric field lines from the origin, from the source, they move to the infinity, whereas here they end. So the electric field lines start from infinity and they end at the source charge. But in case of a pair of charges, positive and negative, in this case the electric field lines move from positive charge to the negative charge, right? Suppose if I have a plus 4 units of charge and minus 1 unit of charge which are separated. Now, let us consider very close to the negative charge, very close to the negative charge, what we have. So, here, what is the electric field experienced by the test charge very close to the negative charge, minus 1. So, here, the electric field is due to the field because of the plus 4 charge and the field because of the minus 1. So, at this point P, the electric field is due to field due to plus 4 charge plus field due to minus 1. That's nothing but the superposition principle. If you have more than one charge, the electric field at that point will be given by the superposition principle, right? So here, which is more? Electric field, which is more? Here, this positive charge is strongly repelling the unit positive charge, whereas the negative charge trying to attract the positive test charge towards it. So in this case, the electric field due to minus 1 charge is dominated. So in that case, the electric field, if the point is very close to minus 1, the electric field due to the minus 1 unit test charge is dominating than the electric field due to 4 units. So here the electric field is acting in the left side, means that the test charge experiences attraction due to minus 1 charge. Now let us consider the point P which is very far from both the charges. So in that case, what is the net electric field? In this case, here the charge separation is very less compared to this point P. So here we consider this together as a system, So what is the net charge on the system now? The net charge on the system is plus 3, plus 4 and minus 3, minus 1. So it is plus 3. So due to positive charge, which is at this location, the electric field at point is, this positive charge is experiencing a repulsion due to this positive charge. So in this case, the electric field is lying along right side direction. So very close to the minus 1 charge, if I consider an arbitrary point, the electric field is pointing left side. If I consider a point charge far from both the charges, in that case the electric field is pointing in the right side direction. So somewhere in between at one particular point, so see here, this is pointing left and this is point right. So somewhere in between these 2 points, the electric field will become 0. That is called the neutral point. So this is about the electric charges and the electric field lines. And we know that we said that always the electric field lines move away from the charge. If for the case of positive charge, they move away from the charge, and the for the case of negative charge, the field lines are moving towards the charge. So they may be radially outward or they may be radially inward. For the positive outward and for the negative it is inward. And here the electric field lines move from positive to the negative. And we don't have two electric field lines crossing each other. We never expect two electric field lines crossing each other. If they cross each other at one particular point, we have two different directions. So vector have only one direction. It doesn't have any two directions. So saying two directions at a particular point is meaningless. So no two electric field lines cross each other. And we don't have a closed loops. Electric field lines will not be a closed loop in case of electrostatics. See here, these are starting from positive charge, ending at a negative, and again they are not reversing back. So we don't have any closed electric field lines. That is about the electric field lines due to different charge configurations. Thank you.